The curses of putting the videos up on YouTube is that the class attendance tends to dwindle. I noticed this. The more convenient we make it for people to watch videos. Announcements. Let's see. You have a homework due a week from yesterday. So if you really haven't started that, I definitely would suggest that you do. We have lots of office hours. We have a total of 5 office hours each week if you guys need help. And there's also Piazza. Let me just look when the project proposals are due to remind myself. So the project milestone says is due at the end of this month, according to the website, September 29th. If you guys have not thought about that at all, you should also definitely do that. So at this point, you should be contacting other people in the class, trying to form groups of 2 or 3, and starting to, hash out some project ideas. The milestone, which is due at the end of this month, it's not really that big of a deal. We don't give people bad grades in the milestone unless they don't do it. So if you turn in something, even if it's not a very viable project idea, that's the point of the milestone, is for us to be able to give you feedback. So don't stress out about it, but make sure that you do something because we want to give you feedback. If your project idea doesn't really seem very feasible or related to optimization or something, we'll tell you that. Any questions on administrative stuff before we start? No? OK. I wanted to go through a few more slides from the last lecture, really one example in particular that I think is kind of neat. And then today we have a fun lecture on all the various kind of canonical forms of convex programs or convex problems that you might encounter. OK, so we saw this idea last time. I just was going to leave it up on the slide for a minute because this idea of slack variables we're going to see today actually helps quite a lot with reformulating LPs, Qps, SDPs into what we call standard form. So just a quick refresher, if we ever have affine inequality constraints, we can always turn those into affine equality constraints by introducing what we call slack variables. So the general idea is if you have gi of x is less than or equal to 0, you can rewrite that as gi of x plus si is equal to 0, or si is a new variable you've introduced, and you just put a non-negativity constraint on si. These two together are the same as this. But you can see that when gi is affine, this entire thing is just a new affine constraint, equality constraint. So it says that you can kind of get rid of affine inequality constraints in favor or in trading off for more equality constraints and simpler inequality constraints that are just non-negativity constraints. So this was a few other kind of transformations we didn't get to last time for convex problems that I wanted to go over, and then an example. If you give me an optimization problem that's of this form, minimize f of x subject to x being in some set C, which remember we said this is it's perfectly general. This form of the way that we write this can encapsulate all the inequality constraint functions and equality constraint functions in this set. Then if I take a bigger constraint set called C tilde, so if I actually just enlarge the optimization constraint set, then we call this a relaxation of the original problem. That's typically the word we apply to it. And its optimal value is always going to be smaller than or equal to that of the original problem. OK, so that should be clear because we're minimizing f over a larger set. The value we get can only be smaller or equal to. Oftentimes, we do this when the original constraint set is not convex. So we would call that a convex relaxation. For example, we might take the convex hull of C, and that might be our C tilde. That would be called a convex relaxation of our problem. And what we know in doing that is that the optimal value can only get smaller, or it can stay the same. OK, that's the idea of relaxing the constraint set in some sense. And a typical case you might consider is when you have non-affine equality constraints. So you have equality constraints, but that aren't determined by affine functions. Remember, we can actually fit this into a convex problem formulation if these aren't proper affine functions. So if we would relax those to inequality constraints, if these functions were convex, that's perfectly fine. We now have a convex problem. But we may have actually changed the problem. It could be the optimal value of this problem now convex is smaller than what it was before. If we're lucky, maybe it stays the same. Right? It just depends on the problem. So I have an example in the slides. We went over this last time in detail, the last version of this course, and we actually had homeworks on it and stuff, but it would turn out to be actually quite a bit more subtle problem than I initially thought it would be. So I'm just going to kind of give you the very high-level explanation of it. If you're curious to learn more about it, go over the slides and homeworks from the last version of this course, or check out Boyd and Vandenberg. I think it's going to be the chapter on just convex optimization, which is probably going to be chapter 3 or 4. I can't remember which one. The one that introduces optimization problems also has an example of this form. The problem that we're looking at, let's suppose, is a maximum utility problem. So it models what happens if you, are trying to basically handle a bunch of investments. And the variables in this optimization problem, let's say, are x and b. And the criterion in this optimization problem is the sum of alpha t u of xt. And you can think about xt as the amount that you've consumed of some good at time t, and u as a concave utility function. So it tells you what you get out of consuming some amount. Alpha t are given to you. They're just think of them as positive weights. So this entire function then is concave, right, in x. So it makes sense to maximize a concave function. And what we can see just briefly staring at this is that these constraints almost look like convex constraints. This almost looks like a concave maximization problem. Okay, except this is the troublesome constraint right here, this equality constraint. So let's just first look at the inequality constraint. We're telling ourselves that the amount consumed at each time point has to be somewhere between 0 and bt, where bt is our budget. Okay, another variable. So you can't consume more than you have available as part of your budget. And then we have this recursive definition for bt, which tells us that the budget at time t plus 1 is what it was at time t, minus the amount that you've consumed, plus some investment return function. So suppose I make some investments with my budget. What I get back out of that is fb of t. So what I have as my new budget is the amount I've consumed, x of t, the amount I've gotten in return from my investments, and what I had before. This should make sense just at a high level, this recursion. And so that this convex, or this nearly convex problem, is trying to figure out the optimal allocation of your budget and consumption over, say, capital T time steps. This is not a convex problem because of this constraint. We didn't tell you that f is an affine function, and if f was not an affine function, then you'd be in trouble, right? Because I have a non-affine equality constraint. I can think of, let's just think of f as a concave function that's increasing, okay? So like, say, square root of x, or square root of bt. That's f of bt. So it turns out with this problem, if we replace the equality constraints with inequalities, then that is a relaxation of the original problem, as we mentioned per the last slide. The new problem is a concave maximization problem, or a convex optimization problem, we'd call it. And the nice thing about this particular example is that it doesn't change the optimal value of the problem. It doesn't actually change the solution either. So to see that, it requires a little bit of manipulation, which is why I decided not to do it in this year's course. You can take a look at the homework. Actually, homework 1 from last year's course goes through this in detail. The intuition is that it doesn't help to throw away money. So if at the solution, for some reason, your budget was just strictly less than what you had before, plus your investment, plus your consumption, that wouldn't be helping you out. So you'd be throwing away money in some sense. So you might as well take your budget as large as you can, determined by the investment, what you had before, and your consumption. So we can always relax that to an inequality constraint, because at the solution, we claim, at least intuitively, this is going to be tight. We're going to see inequality at the solution. So we haven't actually changed the problem. Okay? So that was just a high-level explanation. The idea is a simple one, right? Sometimes we can relax equality constraints to inequality constraints, and if we can argue that they're actually tight at the solution, then we haven't changed the problem. This is the example I wanted to go over more so than the last one. Another example of relaxing an equality constraint. I think it's a really cool one that a lot of people maybe don't see or just aren't familiar with, because we typically think of principal components analysis as being very non-convex. So let's suppose I give you an n by p matrix, and I ask you to form a low-rank approximation of that matrix. And I ask you to solve, in particular, the following problem. Find me a matrix R that in Frobenius norm is closest to x. Frobenius norm between matrices means just the sum of the squares of the absolute values. So it's like the L2 norm but for matrices. Or it's literally the L2 norm if you unravel the matrix into a big vector. So find the matrix R that's closest to x in Frobenius norm but that has rank k. Okay, so this is the best rank k approximation to my matrix X. This is a very kind of well-known problem in terms of PCA or the SVD. The solution, as you probably would have seen in other courses or maybe would have heard, is just to take the singular value decomposition of X, UdV transpose, and to chop it off after the first k singular values. So essentially, you can think about it in multiple ways, but let's suppose I just take the first k columns of U. I only take the first k diagonal elements of D. And I take the first k columns of V as well, which means the first k columns of the first k rows of VK transpose. So I basically throw away everything after the first k singular values. And I form this new product, UK, DK, VK transpose, and I call that R. That is the solution to this problem. Okay, and when the SVD is unique, which happens when there's no ties, let's say, in singular values, then this is the unique solution. So it's pretty cool that we know how to solve the best rank k approximation problem exactly using the SVD. You might also call this its reconstruction from its first k principal components, right? Because if I thought about this in terms of PCA, then the columns of U are the principal component directions. So I'm taking the first k directions that explain the most variance, let's say, in my sample. So I'm reconstructing X from the first k principal components. This is not a convex problem. It's very far from a convex problem. What makes it non-convex? What is it? Sorry? The rank constraint. Yeah. So why is rank not a convex function? Give me an example of why rank is not a convex function. Yeah, sure.
A plus minus A is 0.
It's a good example. So yeah, the example was if I have, let's suppose I have some matrix A of any rank that's, so that suppose A is not trivial, and I take another matrix minus A. If I take a convex combination of those, let's say half A plus half minus A, I'm going to get 0, which has rank 0. It's clearly not going to obey no, actually that's not quite going to work, right? Because what we want to see is that actually the rank gets bigger when we add two matrices. So we want to see that rank of, let's say, alpha A plus 1 minus alpha B exceeds the rank. Right, we want to see this violated. So how would I do that? Yeah.
You have two 2 by 2 matrices. One of the first column is, let's say, 1, 0. Yeah, and that's 0, 0. And you have another one that's 0, 0, and 0, 1.
Right. So that'll do it, right? Because these are each rank 1. If I take any convex combination of them, they're rank 2. But the right-hand side is always just going to be 1. So it's certainly not convex. In fact, the way you can think about the rank on matrices is that it's analogous to the L0 norm on vectors. So it's about as far away from a convex function as you can imagine. So it's very non-convex. Right. So we're going to actually do a few things to manipulate this and to take a convex relaxation. We're going to want to relax this constraint set. So the way we're going to do that is we're actually going to first kind of reformulate the problem in an equivalent form that's non-convex. And then we're going to take the convex hull of the constraint set. So we're going to write this as, find me a projection matrix that's a k-dimensional or rank k projection matrix on which I can project X and then measure the Frobenius norm between X and XZ. It's really an equivalent problem. The solution to this problem would just be VK, VK transpose, for example. So it would be forming the projections from the first k principal components. So it's an equivalent problem. What does it mean for a matrix to be a projection matrix? Let's spell out this constraint set a little bit more carefully. It means that Z is let's say a P by P matrix, symmetric. And there are two kind of defining properties of or there's actually one defining property of a projection matrix besides symmetry. And then the second constraint is to do with its dimension. It's the rank of that projection. A projection matrix always has eigenvalues that are either 0 or 1. So if a matrix is symmetric and it has 0 or 1 eigenvalues, then we call it a projection matrix. And this just determines its rank. The sum of the eigenvalues, in this case, is just the number of non-zero eigenvalues because they're all just 0 or 1, right? So its rank is going to be the sum of the eigenvalues. And so enforcing that trace of Z is equal to K is just saying that Z has to be of rank K. So this is our constraint set. So now that we see this, it's interesting. It's not, at this point, it looks like it's certainly non-convex. It's really the same constraint set as we had before, just reformulated. But we can kind of see what to do. Informally, what happens if we just relax the eigenvalues to be between anywhere 0 and 1, not just 0 or 1? And is that an offensive constraint, the trace C equals K? What is trace as a function of Z? What kind of function is that? Yeah, but what kind of function is that as a function of Z? Just a linear function, right? Just summing up the diagonal entries, so it's a linear function. That should make sense to you. That's a linear equality constraint on a matrix. So that's actually not bad at all. It's just this one. And now we might think, well, let's just relax the eigenvalues to lie between 0 and 1 rather than be equal to 0 or 1. You can check that by doing so, you've actually formed the convex hull of that constraint set. So this might be a good exercise to make sure you understand convex hulls. Prove that that is the convex hull of this. So just by making that an interval 0, 1, we've actually formed the convex hull. We can also rewrite that just in the simpler form. Z has to be between 0 and 1 in matrix inequalities, or 0 in the identity. This means that all of its eigenvalues lie between 0 and 1. This is called the Fan-tope of order K. So it kind of looks like a polyhedron, but it's in a matrix, right? We have some linear inequality constraints on a matrix, and we have a linear equality constraint on a matrix. It looks kind of like a polyhedron. We call it a Fan-tope just because I think it's named after this author Fan, who first kind of studied this object. So to relax that problem, the one we saw before, we can just use this constraint set instead of the one that just considers all the eigenvalues being equal to 0 or 1. And we get this new problem. Find me the projection, or it's actually not a projection anymore. Find me the matrix Z such that XZ is closest to X in Frobenius norm, subject to Z lying in this constraint set, which is bigger than the set of rank K projection matrices, because all these matrices can have eigenvalues between 0 and 1, not just equal to 0 or 1. That's a convex problem because the constraint set is convex. And remarkably, you actually get the same solution if you were to go and solve this than you would to the PCA problem. So you do not lose anything when you make this relaxation. So in a sense, PCA is actually a convex problem, or at least it's equivalent to a convex problem. It's something I think a lot of people don't see. And certainly when I actually didn't know this until a few years ago, when one of my colleagues in statistics came and told me this, that people had figured this out a long time ago, and was very excited about it. And I was shocked, because we always learned PCA as a non-convex problem. Here it's being written equivalently as a convex problem. OK, so this is from 1949. I'm sorry?
Why it is equivalent?
So I didn't give you a proof of why it's equivalent. I just told you that it is. I just told you that in this case, the convex relaxation is tight. It's because here's my extremely rough explanation. This is curved enough, this loss is curved enough, so that the minimizer always lies at a vertex of that constraint set. So it's never going to lie on a, so this constraint set, think about it as a polyhedron for matrices. Its vertices are kind of determined by this set, right? The set of matrices that have eigenvalues equal to 0 or 1. And it works out, if you take a look at this paper, that the solution, if you solve this problem, is always going to lie at a vertex. It's a really nice result. And it started now a whole kind of slew of work on sparse PCA out of some of people in statistics here at CMU who use this as a jumping point for sparse PCA, because now you have a convex problem to sparsify. So if you're interested in that, then you can take a look at some papers by Jing Li and Vince Fu. They have some very nice papers on this. All right. Any questions about that? Yeah.
So for the original PCA, you're using SVD to get the solution, right?
Yeah.
But you see, you can get a convex flow for this problem. So is there anybody like try to solve the PCA using convex optimization?
That's a good question. So you'll see today, actually, from our lecture today, that this is an STP. And I would say, in general, STPs, unless they're very special, are harder to do than a single value composition. They're not a very easy problem to solve. This one, I think, is probably an example of that, falling into like a generally hard STP. So I'm not familiar with people using like interior point methods or something to solve this. But when you do sparse PCA, you need to use that. So there's not like a very simple SVD-like formulation you can use.
Are there any pathological cases where that's not necessarily equivalent? Like, is it equivalent with probability 1, or is it guaranteed always equivalent?
Good question. I actually don't know. I would guess that in pathological cases, this has multiple solutions, and one of them is going to be a solution to the PCA problem, but I don't know for sure. I would take a look at either this paper or some of the newer ones. Yeah?
So what's the advantage of using these formats compared with the canonical protocol? You have a constraint of W so such that you use like Lambda multiplier and basically prove the W, the original form put into PCA.
I'm sorry, I didn't really understand the question. Proof meaning that the PCA, that the SVD gives you the best rank approximation?
Like you could have a covariance matrix of the data and use W transpose covariance matrix times W. You want to maximize that such that the W transpose W equal to 1.
So that's like a sequential way of looking at PCA. Find the first principal component direction, the second principal component direction, et cetera. Yeah, this problem is telling you what they all are at once. It's just it encapsulates that the first case, that's that problem into one optimization formulation.
So is it like in the future, if you want to prove any like low rank approximation problem, maybe this is a better way to do it?
Well, the fact that it's convex is a big win. So I said this, maybe I said it rather quickly. People didn't really realize that this fact was true, I think, or didn't appreciate it until a few years ago. So there's been a lot of work on sparse PCA. How do you get principal component directions that are sparse? But everyone went from the non-convex formulations in order to sparsify the criterions. So for a long time, I'd say probably 10 years, people were taking the sequential problem, the one you mentioned, or the rank K approximation problem, and they're adding kind of sparsity constraints. But they couldn't really do much with it because the problem wasn't convex. So the solutions that they were finding were all locally optimal. And it's harder to characterize also theoretically what you get out of it because it's harder to understand non-convex problems. When people realized that PCA was equivalent to the convex problem, namely this one, sparsifying it is actually much, much easier, right? I can add an L1 penalty at this point to Z, and that still is a convex problem. So both computing the solution and also understanding its properties became a lot easier. So it kind of led to a breakthrough, I think, in sparse PCA. No, yeah. So yeah, good question. So once you apply a penalty, the solution is going to lie somewhere not generally on the vertex of that constraint set. So it's no longer going to be equivalent to the exact rank K formulation. Yeah, there's like a strict discrepancy. Good question. All right, cool. So let's get to canonical problem forms. I think this is going to be a fun lecture. So last time we went over, I mean, I'll just very briefly say it, optimization terminology, properties, and first order optimality. This was like the big thing we learned, how you can characterize the solution to a smooth convex function if it's to a smooth convex problem if the criterion function was smooth. Remember we had a formulation for that. And then a bunch of equivalent transformations that we saw at the end, including relaxations, which we just talked about. So today we're going to talk about LPs, Kewpies, this is SDPs, and cone problems. And when I taught this class last year, I had this particular lecture, I had Javier Pena, who's an optimization expert in the business school, give a guest lecture, and he drew this cool picture, and so I want to redo it. I thought it was a motivating picture. I may even make it a bit more dramatic than him, just to one-up him. So here, let's suppose this is the world of LPs. Okay, so you're happy and you can solve all these LPs. Turns out that LPs are a special case of Kewpies. Okay, so this might be what it looks like. And by the way, there's nothing rigorous about this picture. This is completely hand-wavy. But it gives you a sense for the lay of the land. Kewpies are a bigger problem class. They are substantially harder than LPs. And you'll see examples of an LP and a Kewpie, and you'll see that actually the Kewpies that we mentioned can be pretty hard. Then there's SDPs. And SDPs kind of look like this. So this is really the big difference. The jump from Kewpies to SDPs is massive. SDPs are a way bigger problem class, and they are way harder than Kewpies. So there's really no comparison. A generic SDP is very, very hard to solve, even though it's convex. Okay, so I would say, heuristically, an SDP with more than 1,000 variables is getting to be almost intractable, unless it's a very special SDP. Whereas an arbitrary QP, we can handle for hundreds of thousands of variables. It's not a problem at all. Okay, so SDP is a lot harder. And then there's conic programs, which are even bigger than SDPs. If you use CVX, which you are going to learn to use on the first homework, if you use some like optimization solvers like Sedumi, these other kind of general purpose optimization solvers, they formulate everything that you give them as a cone program, and they solve it. So this is where I think things get hand-wavy. This so far was, obviously there's nothing rigorous about these sizes, but I think this is intuitively more or less the case. I would claim that cone problems are very close to the set of convex problems. It's pretty hard sometimes to find convex problems that aren't cone problems. I mean, you can find examples, but like I said, general purpose convex solvers turn everything that they can into a cone problem, and they're very successful at doing so. You can usually use CVX or something like that for almost any problem that you might encounter. So I'm going to draw this as a dotted line because I'm not really sure how big to make it. But somewhere out here is the set of convex problems. Okay? And then just to give you some perspective, this is maybe the set of convex problems among the set of non-convex problems, or just optimization problems in general. So it's kind of like if you were studying the stars or something, and somebody showed you Jupiter next to Earth, and you were blown away. Then they put the sun next to Jupiter, and you kind of lost it. That's what's happening here. So we're not really solving that many problems in the grand scheme of things, but this is the hierarchy nonetheless. Okay, so that was my picture. So let's start off with LPs. A linear program is an optimization problem where the criterion, the inequality constraints, and the equality constraints are all linear functions or affine functions. Okay. This type of problem is always convex. You can't make it non-convex no matter how pathologically you try to choose these matrices or these vectors, right? Because I always have an affine criterion, which is always a convex function. I always have affine inequality constraints and affine equality constraints. It always makes a convex optimization problem. I can have this being a min or a max. It's still going to be a convex optimization problem. Okay. I think people remembered Danzig for LPs in the 1940s. Danzig was the guy who invented the simplex algorithm, became very famous for that, among other things. But so I'm told Kantorovich actually studied LPs earlier than Danzig in the late 1930s. We're not going to learn the simplex algorithm in this course. We taught it in previous versions, but I just didn't think that it was something that people really got a lot out of. It's a very beautiful algorithm, but it's very specialized in a sense to LPs. The one thing that I would say it's important to note about it is that it's a direct algorithm for solving LPs. So pretty much everything we're going to learn, starting when we talk about gradient descent onwards, so all the algorithms you're going to learn in this class are what I would call indirect or iterative algorithms, which means that you iterate the algorithm, and as you iterate, it gets closer to a solution, and you get some guarantee such that if you wanted the points you're going to settle on to be epsilon close to the solution, you need to take this many iterations. Right? So in the limiting case, you're going to get the solution exactly, but you're going to be kind of epsilon away after 1 over epsilon iterations, that kind of thing. Direct algorithms are different because they give you the exact solution of the problem up to computer precision. So it's a very different class of algorithm. In a perfect computing environment with no kind of overflow or round-off errors on a computer, the simplex algorithm would give you the exact solution to an LP. But say an interior point method wouldn't. It would never give you the exact solution because it's iterative, and it would just get you closer and closer, even in a perfect kind of computing environment. Okay, so that's the distinction. Sometimes people prefer direct algorithms if they really want a super high-quality solution. We won't see very many of them because they tend to be specialized. So this is a very fundamental problem in convex optimization. It was kind of the original problem that people spent a lot of effort studying. There's lots of history and diverse applications of it. I'm just going to go through a few simple examples. The diet problem, I think it's a fun example. Let's suppose that x is a variable that contains the units of food for each kind of type of food you're going to be consuming as part of your diet. So xj is the units of food j that you're going to consume. So let's consider this problem. Minimize C transpose x subject to an inequality constraint. Dx is bigger than or equal to little d, and x is bigger than or equal to 0. So this makes sense, right? You can't consume negative units of food, or at least that would be pretty bad if you were doing so. Let's suppose that another constraint is that for each nutrient I, you need to get that many nutrients in order not to get sick. Okay, so you don't want to just eat Cheez-Its all the time, even if you find them delicious, because you can get sick. So you have some constraint that you have to actually consume so many nutrients. Then each row of D is going to basically tell you how much you get out of consuming the various food types of that particular nutrient. So that's a nutrient requirement. And Cj is the per unit cost. So this is just saying I want to spend the least amount on food subject to meeting all my nutritional requirements. So classic problem for LPs. The transportation problem is also a classic problem for LPs. I'm just going to skip it because we have lots of examples. But this one, I think, was a problem that people actually studied for practical reasons when LPs were first kind of coming out. Here's a non-trivial problem that fits into, I mean, these are also non-trivial, but here's a problem that fits into LPs that maybe you might not see right away why it's an LP. Let's think about solving a linear system of equations. So x beta equals y, where beta is the variable, and asking for a sparse solution to a linear system of equations. And in order for this to be interesting, we're going to assume that that system's underdetermined. So there's multiple solutions. We want to find a sparse one. The sparsest solution to a linear system of equation would be given by solving this non-convex problem. Minimize the L0 norm of beta subject to x beta equals y, where the L0 norm just counts the number of non-zero elements in that vector beta, right? So that makes sense why that's the sparsest solution to the linear system. The L0 norm is not actually a proper norm. We just call it the L0 norm, I think, being casual, but it's not a proper norm. So this is not a convex problem. Like we said, the L0 norm is very far from convex. I don't know if we ever explicitly stated that. So maybe I'll just write it down. The L0 norm of beta is the sum of the indicators that each component is not equal to 0. So let's suppose beta was p-dimensional. That's the L0 norm. Okay, so now you can see why it's so non-convex. think of the same example we have with matrices, basically. So the L1 approximation to this problem is often called basis pursuit. I just replaced this L1 norm with what I saw previously. I mean, I placed the L0 norm with this L1 norm. And this goes by many names, but some people call this the basis pursuit problem. We saw the lasso, right? This is almost like a noiseless version of the lasso. So I assume I have no noise in my measurements, so I actually do observe the target directly, and I want to find beta, the coefficients that make this equality true, but also have the smallest L1 norm. This is actually an LP. And it's got a lot of attention when people started studying compressed sensing, and even now, it's an LP. So how do we see it's an LP? We can reformulate it in a way that makes it transparent that it's an LP. We're just going to introduce an extra variable, okay, that's of the same length as beta. Let's call it z. And we're going to require that z be between right, that z be bigger than or equal to both beta and minus beta in each component. Okay, so only one of these constraints is ever going to matter, and that's going to be whatever one that corresponds to the sign of beta in that component. Right, so this is effectively saying that z has to be bigger than or equal to the absolute value of beta in every component. But formulated this way, we clearly have a bunch of linear inequality constraints, which is what we wanted to do. We're going to replace the L1 norm of beta then with just the sum of the entries of z. And I actually claim these two problems are going to be equivalent. So check that makes sense to you. Think about why that's the case. So that's going to be the case because it's never going to be helpful to take z to be strictly bigger than the absolute value of beta in any component, right? Because that's just going to make the criterion bigger, and the constraints would be loose at that point. So if you ever had such a solution, I would just take z to be equal to the absolute value of beta in that component. I would make the criterion smaller, and I would still be feasible with respect to the constraints. So I would have gotten a strictly better candidate than your original proposal, which tells us that actually at optimality, z is going to be basically equal to the absolute value of beta in each component. So these two problems are going to be equivalent. Yeah?
So the reformulation makes sense to me. I was just wondering, why is the first one not already a linear program? I have missed that.
Linear programs have to have the criterion and the constraints all being linear functions. This is not, right? This is the sum of the absolute values. So, I mean, as you can see, you pretty much can always transform absolute values into linear functions, but as we've written them, they're not. Another example of an LP is the Danzig selector. So now this is like getting towards what the lasso does. So allowing for imperfect measurements. Let's suppose we didn't actually think that the y we measured was exactly x beta. There was some noise. And we want to find some beta so that x beta is close to y, but beta is also sparse. This is the same problem the lasso tries to solve. But the lasso we're going to see is actually a Kewpie. The Danzig selector is a version of kind of sparse regression that is an LP. It's still an LP. The Danzig selector was named after Danzig, but it was invented recently. It wasn't something that Danzig himself studied. So basically, all we do is we take this equality constraint in the basis pursuit problem, and we replace it by the following inequality constraint. The infinity norm of x transpose times the residual y minus x beta should be smaller than or equal to lambda. So that tells us that for every component, I should have, for every column, let's say, of x, I should have this being true. The equivalent constraint for all columns of x. Because the infinity norm is just the maximum absolute value. This is saying that the inner product of every column or every feature, say with the residual, should be at most lambda. When we have the least square solution, this is going to be 0, right? So now we're just allowing for a little bit of slack there. When we have the linear, the beta that solves this system of linear equations, this is going to be 0, obviously, but now we're just allowing for a little bit of slack there. OK, this is still an LP. We can reformulate it in the same way as the last slide to take care of the criterion. This constraint actually can just be reformulated in one more step in the following way, right? As a set of 2p linear inequality constraints in beta. So Danzig selectors, I think it's a pretty neat estimator. Lambda is a tuning parameter here. It kind of controls the trade-off between how well you want to fit to y with x beta and how sparse you want to make beta itself. Yeah?
What advantages has the loss of formulation?
That's a tough question. Maybe we can talk offline about that. I think that, so the question was, what advantages does the lasso have over the Danzig selector? I'm also a bit biased because I prefer the lasso. But it's actually easier to compute the lasso, let's just put it that. Even though this is an LP, this is actually a harder LP than the lasso. It's kind of bizarre. So in many ways, the lasso is easier to compute. They have basically the same theory. When this paper came out, it proved a bunch of properties about the Danzig selector that made it look really amazing. And then it spurred everyone to prove those same properties for the lasso. So it was very good, I think, for the community. And I think it's a pretty neat idea. Yeah, so we can talk more about it afterwards if you're curious. OK, a linear program is said to be in standard form if you have a big set of equality constraints, ax equals b, and just a very simple inequality constraint, x bigger than or equal to 0. Any linear program can be rewritten in standard form. And the way you do this is to use slack variables. So I'm going to leave this as an exercise for you guys to check. Go to this formulation for LPs, this one. Introduce slack variables here. So dx plus s is equal to d. And then work that into a problem of this form. You'll see that it's possible just by introducing slack variables. So the simplex algorithm, for example, operates on this form of the problem. This one is often easier to remember. The dual of this problem is very easy to remember. It's just nice to work with standard form LPs, as it is with most problems, most of these classes of problems. OK? OK, so now we're going to move up to Kewpies, one step up from LPs. Kewpies are like LPs, but the criteria of Kewpies is our convex quadratic functions. So I will not distinguish, in terms of nomenclature, convex quadratic program or quadratic program. I'm always considering the Kewpies we think about to be convex in this class. But as we saw last time or 2 times ago, this quadratic function, C transpose x plus 1/2 x transpose qx, in order for that to be a convex function, q needs to be positive semi-definite. So you could write down a problem of this form where q is not positive semi-definite, and it would not be a convex quadratic program. Okay, but since we're just not really going to study those, I'm just going to call, when I say QP, I kind of implicitly mean that q is positive semi-definite. All right, QPs allow you to express everything that you can express with an LP and more, right? Obviously, if we take q equals 0, we get back the LP, but we just get more than LPs. I have a few examples here. I guess I have 3 examples of QPs here. We might not go through all of them, but I'll try to give you some that are kind of classic optimization examples. One of the classic optimization example is portfolio optimization for QPs. So x is a variable that contains your portfolio holdings, let's say, in terms of percentages, or actually, in this case, proportions. So like 0.1, 0.15, whatever, for each different portfolio. And the constraints are that the proportions have to sum up to 1, and the proportions have to be non-negative. So those are very natural constraints for proportions. And given these constraints, we want to maximize 2 terms. The first is something like our expected return if we were to invest in those each of those different holdings with that proportion. So let's say mu is the expected return for each particular thing we're trying to invest in. And so we want to maximize the inner product of u and x. That's going to give us high expectation in terms of return. But we're going to subtract off something that has to do with the variance of our portfolio. So if Q is the covariance matrix of the asset returns, then x transpose qx is something like the marginal variance you'd encounter across all those investments. And so this trades off having a high expectation with a low variance. Right? So I'm maximizing mu transpose x minus gamma over 2 x transpose qx, where gamma is just some tuning parameter. So you're like, think about like a risk aversion parameter. Okay, so this is called Markowitz portfolio optimization. And people study this, I suppose, in finance, but I think it's a fairly basic problem. But it's a QP. That was the important point. It's a QP, right? Because we're maximizing here the negative of a convex quadratic function, so we're minimizing a convex quadratic function. OK, what's another example of a QP? I guess we have 2 more examples. I'll just say that these are QPs, and then you can check them. This one, actually, you can see almost directly it's a QP. The SVM problem we saw last time is a QP. It's because the criterion is a quadratic in the variables. I have a linear term in psi, and I have a beta transpose beta term. And all of the inequality constraints are all linear. Right, so this is also a QP. And the lasso is also a QP. I can see that in a couple of ways. So there's 2 ways to formulate the lasso problem. Last time we learned it like this: minimize the least squares error loss between y and x beta, subject to an L1 norm constraint on beta, where S would be my tuning parameter. An alternative way to parameterize the lasso is to use what we might call Lagrange or penalized form. When we learn duality, we're going to learn why these 2 are equivalent, so that for every value of S, there is some value of lambda that makes the solutions the same, and vice versa. So we'll see that formal equivalence later. But this is something that you may be just comfortable with, the idea that you can always take constraints and add them to the criterion with multipliers, Lagrange multipliers, in order to get an equivalent problem. And you can see that either of these are actually QPs. Okay, so I'll leave that for you to check. This one is going to follow the logic we had for the basis pursuit problem. You're going to want to turn that into a 1 transpose z. And this one is going to be doing something similar. You're going to want to introduce some variables that have to do with the signs. Okay, but you can see that both of those are QPs. Another way of saying that is this L1 norm constraint, it's a polyhedron, right? So it's going to be given by the intersection of a bunch of half spaces. So if you enumerate those half spaces, there's just going to be a bunch of linear or affine inequality constraints. OK, QPs can also be written in standard form. It just is the same as what we saw for LPs. They can always be written in a way such that their constraints are AX equals B for a matrix A and vector B, and a non-negativity constraint on the variable x. It's often convenient to write QPs in this form, again, for the purposes of maybe duality or sometimes algorithms, things we'll study later. Let's take a quick break, and then we'll come back and we'll do SDPs.